Hi, I'm Sanjeev. We are in the laser lab in Willis Annex. This is Olivia. Do you want to give a quick introduction of yourself and what you do?
I'm Olivia. I'm doing research in arteriovenous fistula failure. So I'm working with surgeons in the Prince of Wales Hospital, in which we try to see how we can help patients' life by predicting when this the arteriovenous fistula, the AVF, fail. Yeah.
Okay, so that's why do you look into failure? Is because of that? Trying to figure out when it fails or?
Yeah, so trying to see when and what factors that might affect arteriovenous fistula, AVF failure.
Yeah,
So that's basically the goal of my research.
cool.
Yeah.
So how are you trying to see when and why the arteriovenous fistula fails? What's your procedure?
So because I work closely with the surgeons there, so I will be able to have patient's geometry. So basically what I do is I do ultrasound scan on patient, and with the ultrasound images, I am able to get the STL, the 3D geometry that I'm able to use it for CFD, computational fluid dynamic analysis, in which where I look at different parameters that might cause AVF failure in the hemodynamic sense.
So STL was like a virtual kind of model of the fistula, like the
Yeah.
actual fistula.
So it looks like a 3D model of fistula.
Okay.
Yeah.
How do you? What does a scan look? What does the ultrasound scan look like? How does the ultrasound scan turn into a virtual model? Like, what's the process? Like, can you
Yep.
show?
So we start by getting 2D images
Yeah.
from the ultrasound machine. So with the 2D images that look something like that, I segment it based on the vein and the artery.
Okay. So
And-
segmenting means like picking certain points in
Yeah,
each scan.
picking certain points on the ultrasound images, and with that, so the way I pick different points is by looking at the grayscale of the image.
Okay.
And with that, I convert it to a 3D geometry.
Yeah.
So this is one of the geometry that I have, one of the AVF example. Yeah.
Okay. Cool. And then you run CFD on this, is it?
Yeah,
Yeah.
so then I do CFD analysis on that.
Yeah.
Analysis is essentially trying to see how the fluid dynamic of in the vessel will affect, or basically looking at different reasons, different flow patterns of the flow in the vessel.
Okay. Okay. So all in this. So now you've taken the real life into the virtual.
Yep.
What does it look like though? What does it look? How do you visualize it? Like, if you could show
Yep.
us.
So this is one of the example of the geometry. So the CFD streamline, velocity streamline that I have. So if you can look at this image, there's inlets, two inlets. That's the boundary conditions, and you can see that flow is flowing out from the vein. So essentially, CFD is that we put in different inlets, different boundary conditions, and the boundary conditions is it's the same as the patient. So basically, the velocity of the blood is the same as the patient when we took the scan.
Yeah.
So it's trying to make it more patient-specific because it's quite important for AVF to be patient-specific in that sense.
Okay. So this looks like it's showing the blood. So is that all you look at, the velocities in the blood, or is there other aspects?
So this is the velocity. We also look at the washer stress.
Okay.
So this is one of the example of how we look at different washer stress. So we look at OSI, time average washer stress, trans washer stress, and in which, so trying to see how washer stress will affect AVF or, causing different diseases in the AVF.
Okay.
Yeah.
And you seem to be tracking. There's a graph as well. What does the graph show?
So the graph gives us information of what is so for example, this transwasher stress, we have information of how the transwasher stress varies across the center line from the anastomosis. So the anastomosis is the connection of the artery and the vein.
Okay.
Yeah.
And so essentially along the vessel, is that?
Yeah, along the vessel,
Yeah.
yes.
Okay, cool. What is all this equipment? What does it do? What do you use it for?
Yeah, so this is the system that we bring up to the hospital every week to get patients scanned. This is the ultrasound machine. That's the camera. and the camera captures the rigid body at the probe, and the probe is the one that we use for ultrasound scans.
Yeah.
And that's all connected to a computer.
Okay.
So, yeah.
Cool. So how do you get? So this is actually the system that you used to get those scans that you showed us
Yes.
previously.
Yeah, that's
Okay.
right.
So how do you get it? Like what? How do you get the whole arm of a whole vessel of a patient?
Yeah, so essentially, yeah, maybe I can try on
Yeah,
you. So
yeah.
what we do is we do ultrasound scan on the forearm of the patient,
Yeah.
in which where the AVF is at. And with that ultrasound scan, we will have 2D images,
Yeah.
slices of 2D images. And so that's how we get the geometry, right?
Okay.
And then to get the velocity, because remember we have to have it patient specific and it needs to sync with what the blood flow is at the patient at that point of time. So we do we capture the Doppler of the patient,
Okay.
and that's basically the velocity of the blood flow of the patient at that point.
Okay.
So this is one of the example that we have.
That's
yeah.
the purple stuff, is it? That shows
Yeah,
the velocity.
this purple stuff is the velocity of the flow of the blood.
Okay.
Yeah.
Okay, with the heartbeat or something.
Yes, so if you look at the green one, that's the heartbeat of the patient,
Okay.
in which we capture it with ECG. So that's important because then we want to sync it with the Doppler information that we have, and putting it at different boundaries of the computational model.
Okay, because there's so many inlets, you want to
That's
sync
right.
everything.
Yes. So
okay.
we have to sync everything together.
Okay.
Yeah.
You showed me this. You said something about rigid body.
Yeah.
What is it? What does that do?
Yeah, so this rigid body, so if you look at the camera actually tracks the rigid body.
Okay.
That's how we locate the vessel of the patient.
Yeah.
So that's basically the idea of getting the camera to locate the rigid body, and that's how we locate the patient because we scan the AVF, and that's we can know the location. Yeah.
So that means when you're moving, this camera knows where this probe is, essentially.
Yeah. So the camera will be able to track the probe.
Okay, that's pretty cool.
That's right.
Yeah. So all this is you take it to the hospital, or?
Yeah, they are all very portable. We can all put it in a suitcase and then just bring it up, do a scan, and bring it back down. So it's pretty convenient.
Yeah, that's pretty cool. That's pretty cool how it's easy to use all this in the hospital.
Yeah.
What are the challenging aspects of all these components in your research?
So I guess it's so we start by taking a clinical problem from patients, so getting the geometry and stuff from the hospital, and then converting it to an engineering problem where we do computational fluid dynamics, do different simulations, different analysis to see how engineering knowledge can help with a clinical problem. So I guess getting the accuracy of a clinical problem to the engineering and then bringing it back to clinical perspective requires quite a bit of accuracy and precision. So I guess that's one of the challenges in trying to make it as close to the patient condition as possible.
Okay.
Yeah.
So essentially trying to take a problem from the hospital and then putting it back in, which is
Yeah, that's right.
Yeah. Okay. So all this research, once you're done, or once all this research is done, where do you see your research going forth from there?
So I think because we are getting heaps of data, and all this data will be really useful with the artificial intelligence and machine learning coming in, and the rise of different computer vision and computer work. It'd be good to see how that could also come into place, and seeing how I can look at correlations and predictions of AVF with the knowledge of computational machine learning and stuff like that. So that would be quite cool to see how that can help with a further prediction for my work, essentially.
That's
Yeah.
pretty